Dear colleagues, it is a pleasure on behalf of NT-MDT Spectrum Instruments to welcome you all to our first this year's event, the webinar AFM Integration with Light Spectroscopy, Challenges, Advantages and Solutions. My name is Stanislav Leisment. Today I will be the moderator of our webinar. I would like to introduce you our today's presenter, Dr. Artem Shalaev. Artem is the Senior Application Scientist specializing on Raman, SNOM and other optical applications. If you have any questions, we ask you to please to use the GoToWebinar question panel to submit them, and we will we'll try to answer as many as possible of them in the end of our webinar. So Artem, let's begin.
Yep. Thank you, Stanislav. Good day to everyone. Thank you for joining this webinar. Today we will mainly focus on AFM integration with laser spectroscopy. And AFM company has originally started as an NT-MDT company has originally started as an AFM company more than 20 years ago. And by this moment we have a large variety of different atomic force microscopes, which fits for educational needs, for analytics, and for research purposes. But with just pure AFM techniques, sometimes it's complicated to evaluate your samples, to perform investigations. And starting from 1999, NT-MDT has introduced a combined system, combined AFM and confocal Raman spectroscopy system, which right now has second generation, and it calls Integra Spectra 2. So the general optical scheme looks like this. We have an AFM, or not only AFM, STM or scanning near field optical microscope probe in the center, and from top, from side, and from bottom illumination we can excite and collect the light to have precise positioning of the laser spot in respect to the cantilever apex. We can use a piezo scanning XY piezo scanning mirror equipped with closed loop, and to scan by sample we can use XYZ scanning stage. As I said, we can use not only AFM standard probes but also SNOM cantilevers and STM tips. And to detect, we can use confocal Raman spectrometer, fluorescence spectrometer, also photon counting, PMT, avalanche photodiode. We can use lock-in detection scheme, which allow us to detect at higher frequencies of tip oscillations, also gating of photon counting, which is also important for fluorescence lifetime imaging. And we can do laser confocal microscopy. Here, the general optical scheme of the spectrometer coupled with atomical force microscope. And we can see on the optical table on the right-hand side, this is a typical example of spectrometer, which is connected to the lasers, which is coupled by optical fibers with lasers, and then the light goes to the light input-output system. So by several moves, by kinematically mounted holders, you can switch between different excitation channels. And as I said, we can use any of the channel, top illumination, side illumination, and bottom illumination channel to excite, and again we can use each of these channels to collect the optical response of the sample. Here is the flash animation of the light inside the spectrometer, and there is a different laser light sources which can be coupled into the same system. Up to 5 lasers can be used. Then each of these lasers, they go by the same light path. They go through neutral density filter. Then there is a beam expander to make a beam collimated and to be able fit perfectly to the entrance aperture of the objective, and there is an automated switching between different edge filters. So light can be also controlled in terms of polarization. There is a motorized lambda half plate which change linear angle of the linear polarization. Also there is a motorized analyzer which make possible detect Raman scattering signal at different polarization angles. And in the spectrometer itself, there are 4 different gratings with different dispersion, which are covering different wavelength range at a moment. And not only CCD can be used to detect, but also avalanche photodiode to collect fast Raman mapping. This is again the optical scheme of the system. So this configuration allows to get true pinhole configuration allows to achieve 200 nanometer spatial resolution, which is diffraction limited resolution. Also, lasers can cover from UV up to infrared range up to 1064 nanometer wavelengths, excitation wavelengths, and to detect we can use near infrared gallium arsenide detectors. So this is quite powerful system, and this is example of the sensitivity with 10-second acquisition time and 15 cycles, 15 number of exposures. We can easily resolve the 4th order of silicon peak. Another important option which can be used is break volume filters. Such filters allows to get the laser line to get the spectroscopy both stocks and anti-stocks as close as 7 or 10 back centimeters, and therefore it is possible to get Raman signal which is below 100 wave numbers at which value usually cut off of standard edge filters. This is a scheme of the internal design of the AFM head. You can see there is a tip holder in the middle, in the center, and focused light comes from different directions. Each necessary modules like photodiode, laser, and tip position can be adjusted by software, and by mouse click it can be positioned in a proper positions. Also different numerical aperture objective configuration can be used, depend on your needs. If you need to excite from side with a very tiny focused spot, it is preferably to use high numerical aperture objective from side, and then you can collect either by 0.28 numerical aperture objective from top, or using some bottom collection objective. This is how the optical image by top illumination and collection scheme looks like. So there is a tip from this in the center, a triangle shape of the tip. A red spot on the top is beam deflecting, laser beam deflecting system from the AFM, and the black spot in the middle is the tip apex. So using such optical viewing system, you can position the probe onto your sample with about half a micron precision. Now I'm going to show some examples of confocal Raman mapping and atomic force microscopy. And first one is molybdenum diselenide flakes, monolayer flake, bilayer, and multilayer flakes on the silicon wafer. So here we can see simultaneously acquired Raman spectrum, which is on the left part of the spectrum, and photoluminescence excited by blue excitation laser. So near infrared photoluminescence. And when we make a mapping, we can see that monolayer produces a very strong photoluminescence, which is caused by direct band gap. And for bulk materials, there is no photoluminescence because it is indirect band gap semiconductor. And B-layer region is somewhere in between. It shows us very low intensity, rather low intensity photoluminescence. On the Raman signal, we see quite uniform intensity signal, which just demonstrates that there is a material of molybdenum diselenide. And on the topography, we can also see the difference in monolayer, bilayer, and multi-layer regions. Also, there is a surface potential image. Another example is polymer blend of polystyrene and polyvinyl acetate on ITO glass. So the typical Raman spectrum for polystyrene is on the top, and typical Raman spectrum for polyvinyl acetate is on the bottom. Two bottom maps were acquired by the selected Raman peaks, which correspond to PVAC and PS polymers. And from the same area, it was acquired topography and surface potential. So it's interesting that in some regions we can collect signal from polyvinyl acetate, but it does not exist. It doesn't show any contrast on the topography. So this is appearing because Raman mapping, Raman scattering is kind of volume technique. It can penetrate into the sample material and then get a response from the volume of the material. And atomic force microscopy is a surface technique. Another example is a colonia of Cyanobacteria and a biofilm, which is on top of them. So in AFM we can see such image. It is obtained in the water in the liquid, and on the right hand side we can find confocal Raman images of beta carotene, and this pigment appears under the photosynthesis. And another example of technique is genetically modified Escherichia coli bacteria. There are two types of genetically modified bacteria which produces proteins with the fluorescence, but the fluorescence differs not on the spectrum. Spectrum is very similar, just they differ in intensity and also by fluorescence lifetime. So that's how we can distinguish two different type of proteins and therefore two different type of bacteria. Orange color corresponds to the short fluorescence lifetime, and green and blue color corresponds to the longer fluorescence lifetime. This is example of biodegradation of carbon nanotube by a neutrophil by immune system, and after 2 hours, so the nanotube was the neutrophil, it starts to eat the carbon nanotube, and after 2 hours we can find that there is a still sharp peak typical for carbon nanotubes, and after 8 hours there is only broadband peak, which is typically corresponds to amorphous carbon. And this is example from hard disk drive industry. The disk is coated by diamond-like coating, and it's important to evaluate how stable is the coating during the operation. So on this image we can see some scratches on the topography, but fortunately on the magnetic domain structure it does not affect at all. And By Raman mapping, we can find that sp3 hybridization is slightly smaller at such region, and also what is important, we can see intensity of D band and ratio of D band to G band. It increases a lot in this region, which confirms that there are defects in the coating. So the combination of these two techniques allows more complete investigation of the surface. This is example of the correlative PFM, piezo force material mapping with Raman mapping. So black and white lines, black and white stripes, they correspond to domains on the surface with different domain orientation of lithium niobate. And in Raman mapping, we can see bright lines which corresponds to the borders of the domain structure. And if you look to the spectrum, black region, which corresponds to the border, it has slightly different spectrum shape. And here also, which allows to make such confocal Raman mapping and to find a contrast between borders and inner regions of domains. Here we can find photoconductivity, study of the photoconductivity. The sample is microcrystalline structures embedded into the amorphous silicon, which is non-conductive at all, and microcrystalline become conductive under the external light illumination. So the tip was approached, the voltage is applied between tip and sample substrate, ITO glass, and as a result current becomes flowing. So here we can find the top image is a topography, the second image is a local photoconductivity map, a photocurrent actually, under the same voltage, and the bottom image is a Raman mapping. So different type of different phase of the silicon, crystalline silicon, microcrystalline silicon, and amorphous silicon, which is a blue curve. They produces a different shape of the Raman spectrum, and we can clearly see the correlation between these two maps. And the only thing, there are some small region here, which most likely comes from the microcrystalline region completely covered by amorphous silicon. So on this image we can see photovoltaic study. This is multiple PN junction solar cell structure, which was investigated by KPFM to measure surface potential, and the light was excited the potential. So the light was positioned step by step into different PN junctions. Here we have models and experimental data. Top curve is a modeled curve and the bottom one is an experiment under different positions of the laser spot. The left column is for the blue excitation laser and the right column is for the 785 near infrared excitation laser. So we can see a good correlation between experimental and simulation. Another experiment is to identify single vacancies in the nanodiamonds. So on the topography we can get high resolution images of individual nanodiamonds, and on the photoluminescence map we can position at a particular single crystal, and then in the detector channel we can split a signal into two detectors using one-to-one mirror, and we can build autocorrelation curve to confirm that there is only single light source in this nanodiamond. One of advantages of using combined AFM Raman system is that so-called focus track feature. So when AFM probe is engaged into the surface, a laser spot focused onto the same area is always kept in focus. I mean, while scanning without the tip, sometimes laser spot become in focus and sometimes it become defocused for rough samples with a roughness higher than few microns and with tilt samples. So using AFM focus track feature allows to avoid such artifacts, and here we have an example of pharmaceutical tablet and different Raman maps were acquired with tip in and without AFM focus track. Here we have the simulation of localized AFM Raman mapping using a graphene with different number of layers as example. So light is positioned on the tip apex. This is a real-time simulation and it takes only 50 seconds to acquire 100 by 100 points full spectrum map with the spectrum in each point. And as a result, after this 1 minute experiment, we have AFM topography with AFM phase imaging, and simultaneously we have confocal Raman images for example, here it is this is G band intensity, which corresponds to the number of layers. And here, by switching different tips, we can find also, in addition, surface potential of the same flake, also capacitance and local elasticity of the flake. And 2D map, 2D band position map also can be calculated after the full spectrum was acquired. Okay, so this was about a combination of confocal Raman microscopy, which is limited by diffraction limit, and atomic force microscopy. And one of the lack of optical microscopy is the resolution, which is about 200 nanometers and which is much higher, much bigger than the resolution of AFM and STM techniques. And there are some techniques which allows to overcome the diffraction limit by using especially prepared AFM tips. For example, the first technique is so-called tip-enhanced Raman scattering, when we use metallized tip or metal-edged wire to excite locally the electric, to enhance locally the electric field by surface plasmon resonance, and therefore to localize the interaction between the light and sample. In this case, resolution is no more defined by diffraction limit, it is defined by area of localization of enhanced field. The physics inside this process is following. So while the light comes to the laser, to the tip, it produces oscillations of the electron density, electron gas density inside the metal. And such oscillations at certain frequencies, when the laser frequency matches to the material properties frequency, such oscillations, they can produce a resonance and it can enhance the electric field a lot on the tip apex. And what is also important, it's important to have an electric field aligned in Z direction along the tip, not in perpendicular to the tip. So here we can see the modeling of distribution of the electric field enhancement, and typically it is localized on the area correlated to the tip apex curvature. Okay. Okay, let's go here first. So this is an example of point enhancement. Here we have a Fullerian thin film and the tip in, tip out experiment when such a terse active probe interacts with the sample and enhance the Raman spectrum of Fullerian. So we can see in the point we got 5 to 10 times enhancement depend on the particular Raman peak. And another image, another graph, it shows us the dependence of enhancement versus this tip sample distance. And we can see that tip should stay very close to the surface to produce some reasonable enhancement. On the about 10 to 20 nanometers away from the surface, the enhancement decreases significantly. And here we can see a simulation of terse procedure. First, we can see this is an object to study, a nanotube, and we should focus the light onto this nanotube just to be sure that this is proper sample. Then we introduce AFM probe, and now we should focus precisely to the tip apex. This can be done by the scanning, by the laser scanning procedure with the help of the scanning mirror with capacitance sensors. So while the laser goes on top of the piezo, on the carbon nanotube, we can see a Raman nanotube signal, and enhancement appears only in the region at which tip is positioned. So it means that after the image is acquired, we should position the laser spot exactly into this point. And after that, we can do sample scanning to get terse map, nanoscale terse map. This is simulation, and in addition to terse, in addition to map obtained by enhanced signal, we also have a diffraction limited image, which is still appearing because there is a focused laser spot and there is a nanotube on the sample. And depend on the ratio between excited signal and Raman background, this contrast would be bigger or smaller. So for 1D samples, it's rather easy to get nice contrast, nice high quality images, and we can see that first results were obtained in 2007 and they demonstrate about 50 nanometers. After that we got customers who use equipment from an NT-MDT company. They got results about 14 nanometers, 20 nanometers, and so on. And as an acceptance test, nowadays we can demonstrate the resolution about 10 nanometers using carbon nanotubes. As I said, 1D sample is quite easy to study by tip-enhanced Raman scattering because confocal volume does not produce a lot of background signal. And typically we can get enhancement factor of about 30 to 100. When we try to study 2D samples like flakes or thin films, the enhancement factor becomes much smaller. It's about 10 times. And for volume samples, it's even to get 10% or 50% enhancement, it's quite a lot because sample it interact with a full confocal focused laser spot, and the ratio between this tiny terse volume is quite big. So the 3D samples which produce signal from the bulk material, it's quite complicated to investigate by terse. Here we have an examples of 2D sample. This is tungsten disulfide sample on the gold substrate. And here we have a confocal Raman image on the bottom. and there's image on the top from exactly the same area. And just to zoom in, it's shown another region, smaller region, and to get cross-section we can see the resolution is about 40 nanometers, and the enhancement factor here, it was calculated to get about 5 times. Here are some other examples of graphene oxide on the gold substrate. To measure such samples, it's important to be very accurate in the feedback and to stay as long as possible with the interaction with the surface. I mean, to stay close to the surface as long as possible during the spectra acquisition. So for these purposes, we use so-called hybrid mode regime, which allows to be delicate with such samples and to stay about half of the time in a close interaction with the sample. This is example of 3D structure, and silicon germanium lines, they are produced on the top, and we can clearly see the resolution that it is below 100 nanometers. It is about 50 nanometers for such structures, which is quite nice result. So summarizing, we can say that during last 10 years, a lot of groups had successfully achieved test results using different types of the probes, different types of the materials, and we get from such groups, they generate more than 50 publications for TERS application. And another way how to get resolution better than diffraction limit, how to overcome the diffraction limit, is aperture-based techniques. For example, this is a aperture-based scanning near-field optical microscopy scheme. And in this case, we are limiting the area which interacts with the light. Of course, this technique has a significant disadvantage that comes from low transmission of such small 100 nanometer scale aperture. Here we have two main optical schemes for scanning near field optical microscopy. On the left hand side we can see a fiber-based and tuning fork feedback loop system. In this case, bottom illumination is used, and when a luminescent active sample appears under the tip, we can see it by a photo multiplier tube. We can detect photoluminescent signal using such a system. And another configuration, when we excite from the tip, it is shown on the right hand side. Here there is an aperture-based cantilever probe with a hollow pyramid and about 100 nanometer size aperture on the tip apex. And again, this light which interacted with the sample, it can be transferred either to the photoluminescent, either to the PMT or to the spectrometer. And if we put some filter, then we can get photoluminescent SNOM imaging. But also laser intensity can be used as detection signal. And here, this is example of microfocusing device and scanning of the signal layer by layer on top of the surface. This is a simulation on the top right side. And we can see that according to simulation, the best focusing should appear at about 2 microns from the surface. And on the bottom line, we can see images obtained by tip scanning on a different distance from the surface. First it was very close to the surface, then 1.6 microns, and then 2.5, 3.5 microns. So we can find that the best focusing appeared at 1.6 microns, which is in a good correlation with the simulation. And to couple the surface plasmon polaritones. We can also use such technique, such scanning near field optical microscopy. This is example of the interference between two slits here and between such square interferometer for the surface plasmon polaritones. And when the electric field is aligned in x direction, there is interference only in such direction. And when there is a 45-degree incident electric field, excitation electric field, there is appearing also an interference in this direction. So again, the experimental data here, they are in a good correlation with numerical simulation. Local photoexcitation can be important for study of qualities of solar cell quality. So this map is an overlay of photocurrent. Photocurrent appeared by a local light excitation. So at some regions we can see there are quite strong photocurrent, and blue regions, they correspond to smaller photocurrent, which can be caused by lower conversion, light to current conversion. So this is tips for cantilever-based scanning near-field optical microscopy, and we can see the tips can be used not only in a contact mode, but they can be used also for in a tapping mode, which is important for samples which require delicate scanning. And the typical transmission of such probes is about 10⁻⁴, which is enough to get a signal of photoluminescence from, for example, from the quantum dots. Here we can find single point photoluminescent signal acquired in illumination collection scheme, when the light goes firstly through the aperture to excite the quantum dot, and then it was collected through the same aperture and directed to the spectrometer. So IND gallium IND quantum dots were covered by gallium IND cap layer. On the topography we can see only the cap layer topography, and about 60 nanometer thickness of cap layer still make possible to penetrate light into the material and interact with the quantum dots. There are two types of quantum dots. First, they have size about 20 to 50 nanometers in diameter, and another type, they have about twice bigger size, which also affect on the emitted spectrum, because different modes can be excited in a bigger quantum dots. And we can see a blue curve, it corresponds to the one type of quantum dots, and a yellow color curve, it corresponds to another type of quantum dots. And I would like to mention that it takes only 0.1 second per point to get such spectra, and for map of 100 by 100 pixels, it takes about 20 minutes, less than 20 minutes. So another example, here we use uncapped sample. With topography we can find individual quantum dots formed by metallo-organic deposition, layer by layer deposition on the surface. And in this case we cannot use contact mode, because they were moved by AFM probe. So in this SNOM data we have used as a feedback loop mechanism, we have used tapping mode, and it in the same configuration, because sample is opaque, in the same tip excitation collection through the aperture, we acquired such SNOM photoluminescence map, and we can see a nice correlation with topography. There are individual quantum dots and the intensity distribution. And to compare, this is the confocal map of the same, exactly the same region. So we can acquire such confocal map just by removing the aperture cantilever from the microscope. And we can see on this map we cannot separate 3 individual quantum dots, and we cannot identify spectrum from individual quantum dots. On contrary, for SNOM measurements we can do it. And another example of such technique with side excitation and top collection, when it was applied for microdisc resonator. In such microdisc resonator, there are again indium pair, gallium indium pair quantum dots, which produces photoluminescence. And because of total internal reflection, at certain frequencies, it appears, it works as a resonator. Such microdisc works as a resonator, and it appears standing waves. For example, this is an image of TE20 mode of so-called whispering gallery modes, and they correspond to selected sharp peaks on the spectrum. So different whispering gallery modes can be visualized, and also we can, using this technique, we can probe and we can make maps of the selected spectrum of the selected band, which correspond to selected mode of whispering gallery. And this is a diode laser, high power diode laser, and it's important that we can do not only surface measurements, XY cross section is shown here, but also we can do layer by layer XZ scanning, and again it has a nice correlation with calculation with the simulation. So here we can summarize SNOM aperture-based SNOM application, which can be done by NT-MDT instrumentation. And I think I'm going to summarize the webinar. We have discussed co-localized applications of AFM and Raman and fluorescence techniques, which demonstrate a comprehensive AFM analysis coupled with chemical and structural analysis by Raman by spectrometer. And by AFM we have resolution down to 10 or even 1 nanometer with the special probes, and with the Raman mapping we got a resolution about 200 up to 400 nanometers, depend on the wavelengths and depend on the numerical aperture of objective. Also different excitation geometries can be applied and controlled, and we can do such measurements in different controlled environment. For example, in liquid and at heating, sometimes in external magnetic field. Then we have discussed tip-enhanced Raman scattering, and there are data which can be obtained with NT-MDT instrument and with the optical spatial resolution down to 10 nanometers. Different type of the structures can be studied by such technique, and also different type of the probes can be used, not only etched wires, but also commercially available. We can supply such probes, commercially available AFM cantilevers with their active coatings. And aperture-based scanning near-field optical microscopy, it has some limitation about sensitivity, but for samples with strong luminescence, strong optical signal, it can be applied and can demonstrate the resolution down to 100 nanometer. And again, it can be applied for study of lasers, optical fibers, photovoltaics, quantum dots, and other structures, as I said, which emit strong light. So thank you for your time, thank you for your attention, and I will try to answer your questions.
Okay, Artem, thank you very much for your interesting talk. So we got a couple of questions here. You can put the questions to the question folder. And so let's try to answer some of them till we have some time. So the first question, I think it's related to the slide with the cyanobacteria application. So the question is, if you were filtering in time to separate the fluorescence response from these cyanobacteria. The thing is that it might be interesting to work in the same way with several fluorescent proteins. So as I understand, the question is, how did you collect the signal from these cyanobacteria?
And there were two slides about bacteria. First one about cyanobacteria, another about Escherichia coli. So for cyanobacteria, we used just a fluorescence, so it was not filtered. And the data was acquired not by NT-MDT team, it was acquired by group from ATH Zurich, from Professor Renata Zinobi. So it's a fluorescence spectrum. Just the intensity was calculated and mapping was produced by scanning. So I mean, in each point spectrum was acquired, intensity of fluorescence was calculated, acquired by CCD. Then spectrum was analyzed to get intensity in the band about 400 to 500 nanometer, and then it was produced a map of this fluorescence. And time resolve technique was applied for the next slide. So I did not really understand about which sample the question was about cyanobacteria or about the next slide with Escherichia coli.
Well, the question was about the cyanobacteria, but
Okay.
yes, but okay. So another question. You mentioned the TERS application, and the question is, which laser power should be used for TERS?
Yeah, because we should not damage the sample by enhanced electrical field. We should not use a quite strong laser power. Typically, we use about fraction of milliwatts on the sample. 0.1, 0.5 milliwatts is the maximum laser power. Also, it depends on the tip which you are using. If you are using edged wire, you can apply slightly bigger laser power. If you are applying coated cantilever, then in this case you should decrease the laser power because you can melt the thin layer of TERS active coating on the tip. So usually it's less than 1 milliwatt.
Okay, thank you. So the next question, how would you comment the stability of TERS probes? So how long do they live in the air? How long does the tip last? What is your experience?
Yes, we have an experience with such probes. I personally have an experience with gold and silver etched probes. For example, we found that during the weeks they can work more or less okay. And about the AFM probes which we produces last few years and which we use for AFM based TERS mapping. So such tips, they have a guaranteed lifetime about 1 month. And of course, in the first few weeks, we have enhancement maybe 100 up to 200. And by the end of this month, we have maybe twice smaller. but we found a way how to make coated AFM probes lifetime longer, and we got tested a lot of such probes, and we can guarantee there's activity during the months from production.
Okay. Another question is, can you make the imaging of live cells? I mean, in a liquid solution,
Yes, it's
with
possible.
AFM in combination with Raman.
It's possible to make it with an AFM. About the Raman, it's also possible, but the cell should be Raman active. I mean, typically the standard cell, if you take any cell, it will take long time to get a spectrum. For example, red blood cells, it may take you 10 seconds in a point to make a spectrum with a good signal to noise of ratio of the Raman peak. So to make mapping of a living cell, which is typically tries to move, it's challenging. And but there are other cells like cells with beta carotene, like bacteria, which can make they can be fixed, and they can still be living cells. And in this case, it's possible to make even Raman mapping of them simultaneously with AFM.
Okay. And okay, another question: does the topography affect the Raman intensity signal?
Raman, yes, and of course, topography it affects on the Raman intensity. We should focus on the surface, and if there is a strong variation of topography, of course, then we can be out of focus if it is just a pure Raman mapping. I mean, it's important to be always in focus, and then Raman signal depend mainly on the material properties, not on the topography. But if you go away from focus, then due to confocal scheme, we lose some of the signal, and intensity variation, it appears not because of the concentration, not because of the material properties, but because of just a defocusing of the optical scheme. So in this case, if you do not use AFM feedback loop, its effect on the Raman, yes.
Okay, and the next question is related to the AFM feedback loop, actually, and you have mentioned different ways of keeping the tip closer to the sample, and there are different ways like contact mode, like tapping mode, like hybrid mode, and what is the best way actually, and what is the advantages and the disadvantages?
Okay, this is about AFM probes, and of course contact mode, it produces longest contact time and for the strongest enhancement. But if you try to scan being in contact mode, then you can easily scratch away your sample, or you can easily damage the coating, the terse active coating from the tip apex. So in this case, mainly for terse experiments, for terse mapping, it is using low amplitude of tapping mode. But in this case, we still lose the enhancement. And like a compromise, like a mixture of such techniques, it is a hybrid mode. It is like a jumping mode when tip comes to the contact, stays half of the period in contact, and then retract to a few tens of nanometers, 10, 20, 50 nanometers away, and it repeating 1,000 times per second with 1 kilohertz frequency. Such jumping mode, when tips continuously stays in contact, then removes a little bit and go back to contact, it allows to scan with no damage to the sample and with no damage to the tip, because it eliminates all the lateral forces acts to both sample and tip, and also it decreases Ter's signal only 2 times, or even less, because at small distance from the surface you can still have an enhancement. So this mode is preferable to get a stable mapping if the enhancement is not enough to get it in tapping mode. Tapping mode is also acceptable for enhancement of such for such samples like carbon nanotubes and other samples which produce strong Ter's enhancement.
Okay, thank you. I think the last question for today, we are running out of time a little bit, but the last question would be which kind of probe coatings you use, gold or silver, because these materials have different maxima, generate plasmons with different maxima. So what kind of coatings? Yeah.
We are using a mixture between gold and silver. From silver, it gives us a stronger enhancement, and the gold gives us better stability. And also, the coating has some nanocrystalline structure to be stable during the longer time. So the resonance frequency, according to our experiments, it's come closer more to 600 nanometers to the red region, not to the green as it typically for pure silver. So we use a mixture of both metals.
Okay, Artyom, thank you very much for the presentation and for answering all these questions. So as I said, we are running out of time, and we will address the unanswered questions in our further communications. So this year just begins, but we already have planned a couple of online and offline events. So you can follow us on social networks to get the latest information or get the information from our website. Once again, thank you very much for attending the webinar, and see you next time. Yes,
thank you. Goodbye.
Bye-bye.